Now we come to the fourth and final operation with polynomials, which is division. Now, there's actually, I have to give you a heads up, there's actually a couple kinds of division, believe it or not, with polynomials. There's a normal division that you think of, like 12 divided by 6 is 2 kind of division. That kind of division still exists for polynomials, but it turns out that that kind of division leads to some interesting complications and extensions that we're going to save for another day. We're actually going to talk about another kind of quote-unquote division of polynomials. It's actually going to be more useful for us in the short term, and that kind of division is called factoring polynomials. So we're going to take a look at what's called factoring polynomials next. Okay, so what is factoring? Well, let's review. So in our previous session, we learned about how to multiply polynomials. So if I have, for example, x minus 3 times 2x plus 5, I showed you with the box model, by way of the box model, how to multiply that together. And what you get at the end of the day, once you multiply those two polynomials, is you get this. You get 2x squared minus x minus 15. So that's what you get when you multiply polynomials. So that's what we learned in our previous session using the box model, is how to multiply. So multiplication involves taking an original problem that looks like this, in this case, two separate binomials multiplied together using the box model. You multiply them, you get this, 2x squared minus x minus 15. Now, factoring is just the opposite. So factoring is saying, let's start with this as our problem, and I want you to get me this as your answer. So factoring is just doing the opposite of multiplying, really. So it's just going backwards from our answer back to our problem. Okay, so factoring says, let's take this as our starting point. So this multiplied out polynomial, let's take that as our starting point. And your job is to break that apart. Tell me how I can break it apart back into its original two binomials multiplied together. Okay, so it's just like the opposite of multiplying. So multiplying is going from this problem to this answer. Factoring is going back from this as your problem to this as your answer. Okay, so that's what factoring is all about. And like I said, in the short term, factoring is going to be a lot more useful for us than the straight regular multiplication, which is still useful. We're going to eventually learn how to do that. That's going to be something that you're going to learn. But for now, factoring is going to be more useful for us as we look kind of short term. Now, factoring. So how do you go backwards? How do you go backwards from this as your problem to this as your answer? Okay, well, I'm going to show you again using the box model. So we can use the box model kind of in reverse to get our original polynomial or original problem back, multiplication problem back. Okay, now it turns out there's going to be a lot of steps in factoring. Factoring is not, I have to give you a heads up, factoring is not quite as straightforward or as quick as multiplying. Multiplying is relatively, compared to factoring, is going to be a little bit more straightforward and quick. So we've got to learn several layers. There are several layers, like peeling an onion, several layers in the problem of factoring. We got to first learn about something called the greatest common factor. So this is universal to all factoring problems. Whenever you start a factoring problem, you always want to try this kind of factoring first. There's going to be several kinds of factoring. And this is the one you always want to try first. You always want to try to see if you can factor out what's called the greatest common factor, or we're going to often abbreviate that GCF. GCF, or greatest common factor. So if somebody tells you factor out a GCF, this is what they mean. Okay, so what the GCF is, it's related, you probably remember from pre-algebra, the idea of a greatest common divisor, or GCD. It's kind of related to that idea. So the GCD, greatest common divisor, or GCF, I'm going to start to use those terms interchangeably. So when I say GCF, I also mean GCD and vice versa. So the greatest common divisor is the largest number that can divide into both of the things that you're trying to find the greatest common divisor of. So for example, if I ask you, what's the greatest common divisor, or GCD, of 8 and 12? What I'm asking you is, what's the biggest number that can divide into both 8 and 12 without a remainder, with nothing left over? Okay, and that turns out to be 4. The greatest common divisor of 8 and 12 is 4. 4 is the largest number that can divide into both 8 and 12 without a remainder. Okay, you might say, well, what about 6? Well, 6 doesn't divide into 8. There's going to be some left over. What about 8? Well, 8 doesn't divide into 12. There's going to be some left over. So the largest thing that divides into both 8 and 12 without a remainder is 4. So 4 is, we say, the GCD or GCF of 8 and 12. Here's another example, GCD of 18 and 24. So what's the largest number that divides into both 18 and 24 without anything left over, without a remainder? That's going to be 6. 6 goes into 18 3 times, no remainder. 6 goes into 24 4 times with no remainder. Nothing bigger. Maybe, oh, what about 8? Well, 8 goes into 24 3 times with no remainder. Yeah, but 8 doesn't go into 18. So it can't work out that way. So the GCD of 18 and 24 is 6. Okay, now we're assuming that you already know this. We're assuming that you had pre-algebra and that you already know this. If you don't already know about the GCD or the GCF, you want to make sure you let your teacher know so that they can give you some extra things to work with. Okay, but going forward, we're going to assume that you guys already know what the GCD is, what it means to say the GCD. Okay, now we got to extend that idea. So here's an extension. Here's a question for you. What is the greatest common divisor? Let's throw in some variables now. So what if I ask you, what's the greatest common divisor of, say, x squared and x cubed? X to the third and x to the second. What's the GCD of that? What's the largest number? Well, in this case, expression involving variables that can divide into both x squared and x cubed without a remainder. Okay, that's an interesting question. So let's consider that question. Okay, how do we answer that question? Okay, well, let's think about what x cubed and x squared really are. Okay, so if we think about, say, for example, x squared or x cubed, let's start with that one. That means x times x times x. The power, in this case, tells us how many factors of x we're multiplying together. And in the same way, x squared is x times x. Okay, so the GCD is the largest number of x's that they have in common, factors of x that they have in common. That's the most number of x's I can take out of each one without going over. Okay, so if I circle, so they have one pair of x's in common, and they have another pair. That's the most number of x's they have in common, factors of x they have in common. So what you would say is the GCD is x squared. Okay, that's going to be our GCD of x cubed, and x squared is going to be x squared. Okay, and that's because that's the most number of x's that they have in common. Okay, so let me erase that. Okay, so the GCD of x cubed and x squared is x squared. You could also think of it as the smallest power of x of the two. So x cubed and x squared, the smallest power of x is x squared, so that's our GCD. So when you have variables, the GCD is, you can think of it as either the most number of x's they have in common or the smallest power of x. Amounts to the same thing, okay, which in this case would be x squared. Okay, now let's take that a little further. So here's, now knowing that, remembering about the GCD and knowing that about how you deal with variables. Okay, now what if I had this right here? GCD of 20x to the 7th and 45x to the 4th. So now I'm going to combine variables and coefficients, numbers. So if I have a combination like terms like this, I start it in two steps. First, I look at the coefficients, 20 and 45. So what's the GCD of 20 and 45? The largest number that divides into both 20 and 45 without a remainder. And that's going to be 5. So I figure out the GCD of the coefficients, the numbers. Then I tackle the variables, x to the 7th and x to the 4th. What's the GCD of those variables? Okay, well, just like we saw here, you can either think of it as the most number of x's they have in common or the smallest power of x, which is going to be x to the 4th. So the GCD of these two terms, 20x to the 7th and 45x to the 4th, is going to be 5x to the 4th. Okay, so that's the idea of the GCD or GCF, as I'll sometimes call it, greatest common factor. Okay, so what that means is, if I gave you a problem like this, say 20x to the 7th plus 45x to the 4th, the first thing that you always want to do when factoring is try to see if there is a GCF, the greatest common factor. If there is, what you do is you factor it out. It's kind of like dividing it out. factor it out of the original problem. So the GCD is 5x to the fourth. I'm going to write that outside a set of parentheses. Inside that parentheses, I'm going to put whatever's left over from the original polynomial after I divide out this factor of 5x to the fourth, this GCD. Okay, so this is called factoring out the greatest common factor, or the GCF. And this is the first step that you should always do when you have a factoring problem. See if there is a GCF, and if there is, you factor it out. Okay, so how did I get these leftover terms in the parentheses? Okay, well, let's look at the first term, 20x to the 7th. Now, if I divide out 5x to the 4th, first of all, I look at the coefficients. 20 divided by 5 is 4, so that's how I got the coefficient of 4. Okay, then what about the variables? I started with x to the 7th. I'm going to factor out, take out x to the 4th, so 4 factors of x. So that's going to leave 3 factors of x left. So that's how I get the x cubed. Okay, what about the second term, 45x to the 4th? Okay, well, if I factor out a 5x to the 4th, first I look at the coefficients. 45 divided by 5 is 9. That's how I got the 9. And then x to the 4th, I started with x to the 4th. If I factor out or take out x to the 4th, there's no x's left. So all I have left is just the 9. So that's how I got that leftover piece inside the parentheses. Okay, so when I do something like this, start with this, figure out what the GCF is, factor it out, and then whatever's left over, I put it in a set of parentheses by itself. This is called factoring out the GCF, or greatest common factor. It's going to play a role in everything that we do from now on going forward with factoring. So you want to make sure you understand what I just did with this. So if you need to, stop, rewind the video, look it over again, ask questions of your teacher, make sure you understand what this means, how I did from here to here, okay, which is kind of like, remember, factoring is going backwards back to the original multiplication problem. So I'm kind of going in that direction. So to get from here to here, make sure you understand how that works, factoring out the GCF. Okay, and that's the first, and you could say the most important part of factoring is understanding how that works. So now let's put that back together. Let's take a look at how we can take that a step further and factor out things like this. Okay, how do we get to the original problem where things are like that?